10. All of chapter 10 so far has been comparing two samples to each other. This is the only part where it's not two sample. But the reason it's in the chapter of two sample is it is and it isn't two samples. It's what we call paired data. Paired data. Okay? Two separate things happen that we're comparing, but sometimes it's from the same population. So it's not from two separate populations. So paired data, it's like a before and after thing, right? Before and after. Um, whatever data you're trying to compare with. So you could compare data. So as you read these, paired data result from recording two values of the same quantitative variable for each individual or pair, or each pair of similar individuals. So you can be paired with yourself, or you can be paired with someone of similar characteristics. Okay, we've talked about this before, but it's been a while. So to analyze paired data, start by computing the difference for each pair. Then make a graph of the differences. Use the mean difference and the standard deviation of the differences as summary statistics. So we're looking for differences today. Okay, so there are two ways that a statistical study involving a single quantitative variable can yield paired data. So this is the two ways that they gather data. Researchers can record two values of the same variable for each individual, before and after. So an experiment investigating whether music helps or hinders, right? Have you take a test with music, see what your score is. Then have you take a similar test with no music, see what your score is, compared to see if music helps or it doesn't, right? So you're both populations, but you're only one population. So it's compared before and after. Okay? Or the researcher could form pairs of similar individuals and record the value of the variable once for each individual. Observational study of identical twins' IQ scores. Identical twins are virtually the same person. There's very little scientific differences between identical twins. Okay? But there are differences. They're different people, right? So comparing their IQ scores, right? They're different people, but you can compare them because they're very close, right? If I'm trying to test, if I have a supplement that's going to make you lift more weights, right? If you're a weightlifter, I'm going to pair you up with someone who's same size, right? I'm not going to pair someone who's 6'4", 250 with someone who's 5'8", 140, right? They're not the same, right? And if we're talking about lifting weights, it has to be two people who are the same size, right? Because that's strength. So that's one way to do it. So you compare with yourself or you compare with another person. Most of the time it's with yourself because nobody on earth is closer to you than yourself. Okay. So most of the time, most of this data is gathered by pairing before and after, kind of a before and after thing. Okay. So this is where it's tough because deciding whether it's a two sample situation or deciding whether it's a before or after situation because they're completely different things, right? We just did a section 10.2 where you have two separate means and you're comparing them, right? Two separate populations. I have a lot of students who get confused this with that. And if you're doing a test and you think it's two sample and it's not, it's paired data, you don't get any credit because they're completely different tests. So make sure you're running the correct test. So we're going to go over the differences in the questions. Okay. A and B, for example, one are very similar, but one is two sample, which we just talked about for homework. That's a two sample. And one is not a two sample, it's match pairs. Okay. So a researcher wishes to determine whether listening to music affects student performance on a memory test. A, he randomly selects 50 students and each student perform a memory test once while listening to music and once without listening to music. And then he compares the two scores for each student with music versus without music. So is this a two sample or is this a matched pair? So matched pair. Who are the students matched with? Themselves, right? They're matched with themselves. So this is an example of what we're going to see today. Matched pair. Matched pair. This is an example of what we're going to see today. Letter B is what an example of what you've seen before. Okay? They're very similar. He takes 50 students, and half of them perform a memory test without listening to music, and the other perform a memory test while listening to music. He obtains the means and standard deviation of the with music and the without music groups. That one is two sample t-test, which we just covered in the last set of notes and which you just had homework on. Okay? There's key differences between them. They sound very similar. Here's the problem though. If you get this question on a test and you look at this guy and say, oh, it's match pair, and you do a match pair test, that's completely wrong. I can't give you 1 point because you did the wrong test. Okay? So you got to be careful. It's a big deal versus getting the right test. That's one of the hardest parts. Which test should I do? Should I do a confidence interval? Should I do a test? Is it one sample? Is it two sample? Is it match pair? So getting these down. So that's why I have so many examples. The first three examples are which test should I use? Is it match pair or is it two sample? Okay, because it's so important. Like I said, if I gave you this question here, letter B on a test, and you did a match pair test with it, or the vice versa, if I gave you A on a test and you did a two sample test, everything would be wrong. Everything would be wrong. Population parameter would be wrong because there's only one. For A, there's only one population parameter. For B, there's two, right? Hypotheses would be wrong. The only thing you'd get credit for is if you use that, right? Everything else is different. Okay, so just be careful with it. So I want you to do B now. 2A and B. 2A and B. They're very similar, but look for key differences. Are there two separate samples, or is it matched pair? Okay, so this one is a little bit less obvious. Letter A. Just because there's two groups doesn't mean it's two sample. Okay? Doesn't mean it's two sample. I could have one group of students, I could have two groups of students that are similar. Okay? Are you looking at the groups or are you looking at the differences? That's another way to tell. So Mrs. Donald wants to know if the homework load is different in the English and mathematics department at Westbrook High School. She randomly selects 24 students. 12 record the number of hours they spend during the semester on English homework, and the other 12 record the number of hours they spend during the semester on math homework. Is there evidence at 5% that the students who spend more time on math homework than on average in English homework? So are we talking about groups or are we talking about individuals here? There's only one answer. Is it groups or individuals we're looking at? Are we comparing the groups or are we comparing individual times or scores? What's that? The two groups of 12. The two groups of 12. So this would be a two sample t-test. So B, just because two samples A doesn't mean it's going to be match pair for B. So again, she randomly selects 12 who agree to record the number of hours they spend on homework in the 2 disciplines for the semester? Is there evidence that students spend more time on homework, on math homework? So are we focusing on the individual differences, or are we focusing on the groups? There you go. So this is matched pair. Okay. Okay, so we only have one population. It's the differences. One population, it's the differences. Okay? There's only going to be one. It's not going to be two because you're just looking at the individual differences. Okay? So conditions, assumptions, we don't look at the data. We look at the differences in the data. All we're focused on is the difference. Okay. Let's see. Here's for an interval. That's what we're going to use for an interval. This is what we're going to use for a test. This is for paired. On the calculator, you're just going to do a t-test or a t-interval. You're not doing a 2-sample for this guy. This guy is not 2 samples, not 2 groups. It's only 1 sample. Okay? These are the test statistics we're going to use. Okay? All right, let's look at example A, or 4. Okay, read it to yourself. Read it to yourself. That's a lot of stuff, so you can read it to yourself. So data is recorded. We recruit 10 individuals willing to participate in our experiment. Each subject was barred from consuming caffeine during the duration. During the 1-2 day period, subjects took capsules containing their usual caffeine intake. During another 2-day period, the subjects received placebo pills. We randomized the order in which the subject took the pills. At the end of each 2-day period, we had the subject record their headache level. 1 meant no headache at all, 10 meant the worst headache ever. Look at the data. Look at the data they gave us. So they want us to tell, do the data from the study provide evidence at the 5% level that caffeine withdrawals is a real phenomenon? So look at the data. How many sets of data are there? Right? 2 sample, right? It's got 2 sets of data. This is where students run into it. They see 2 sets of data and they're like, oh, it's 2 sample. Here's 1 sample. Here's the other sample. No, that's not what we're looking for. We're looking for a before and after thing. So our data, the data we're going to analyze isn't even up there. Isn't even up there. What is the data we're going to analyze? The difference. The difference. The differences aren't even up there. There are no differences at all here, right? There are no differences at all. We have to create that. Okay? We have to create that. So I'm going to have to create a new all right? So this data is going to be caffeine minus placebo. Caffeine minus placebo. You could do placebo minus caffeine. It's okay too. Just make sure you label it. So the first one would be -1. The second one would be 0, -4, -1, 0, -2, -3, -2, 0, -1. Okay? That's the data I'm analyzing. That's the data I'm looking at. I don't care what their score was. I don't care what the person's score was with caffeine. I don't care what their headache score was with the placebo. I care what the differences were. That's what I want to know. So this is what I've told students to do in the past. Once they do that, do this. Because it just meant there to confuse you. It's just there to confuse you afterwards. I don't care about that. I just care about the differences. That's all that I care about. Caffeine minus placebo. That's all I care about. Okay? So those are the numbers. So really, I only have one sample. Differences. Okay? Those are the ones I'm going to do the test with for A. Okay? So population parameter. It's always going to be sub D. It's always going to be sub D because sub D is the differences. Okay? So the true mean difference caffeine minus placebo headache level. Okay, that's what all those numbers represent. All of those numbers represent, they're a sample of caffeine minus placebo headache levels. So a person with a negative score had a higher headache level, had more of a headache with the placebo than they did the caffeine. Person with a positive, or there is nobody with a positive. Person with a 0, same. Didn't matter. If I took my caffeine or if I didn't take my caffeine, didn't matter. I had the same headache level. Okay? So, hypotheses. There is no difference. It's always 0. It always equals 0. There is no difference. There is no difference if they took the caffeine or they took the placebo pill. No difference. So we have 3 options: greater than, less than, not equal to. So is the difference going to be a positive number? Is the difference going to be a negative number? Or is the difference just going to be different than 0? Let's see, do the data from this study provide statistical evidence that caffeine withdrawal is a real phenomenon? So if caffeine withdrawal is a real phenomenon, what type of numbers should I get, positive or negative? Because
the headache would be higher.
Okay, higher means positive numbers, right?
That means negative number when you subtract the placebo from caffeine, or the other way around the number. If the number is negative, which means the headaches were real.
So if caffeine, so I would expect, if it's real, I would expect headaches to be higher here, right? Higher level headache here means a negative number. Yeah, means a negative number. So less than. Okay. Significance level. It's at 5%. Okay. Conditions, assumptions. Conditions, assumptions. Only one sample. There's only one sample, so we only have to do conditions, assumptions for one thing. Okay. So again, the sample isn't the caffeine levels. The sample is the difference in the caffeine levels. So for these guys, I'm answering about the differences. The differences. So how are each of these guys So was it an SRS of 10 individuals? There you go. It wasn't an SRS of 10 individuals. They volunteered, but order was randomized, right? Order was randomized for each individual. Order was randomized for each individual. So it wasn't, I didn't just get 10 random people. They volunteered. Okay, so N is less than or equal to 10% of big N. 10 is less than or equal to 10% of, well, let's see, 10 individuals. Didn't say men, women, doesn't say anything specific. It just says 10 individuals willing to participate in our experiment. So we just say all individuals. Okay. Okay, just like last time, I have 3 options for the third one. Populations are normally distributed. N is big enough, or I don't have a big enough sample and they didn't tell me, but I graphed the data. So we're going to graph, we need to graph the data. So you're going to graph just the differences. Remember, just the differences. You can make a dot plot, you can make a box plot, whatever you want to do. You can use the calculator to do that just to see if there's any outliers. It doesn't look like there's any outliers because the biggest number is 0 and the smallest number is -4. Those are very close together. Let's see. One, two, three. 3. 1, 2. 1, 1. Missing 1. And -1. No. -2 is 3 zeros. Okay. No outliers. Okay. Okay, test statistic. Differences. Okay, calculations. So okay. I didn't put the average. What was? Do you guys know what the average was for the list? -1.4, and then standard deviation
1.281.
281. Okay. All right. 1.4, 1.281. You can use the calculator to do this, but remember, it's not a two sample. It's not going to be a two sample. It's going to be a regular t-test, to use the calculator to do these. What would be the center of my picture? 0. That's what they share in common with two sample. My sample was negative 1.4. That was the average. I said less than, so I'm going to shade to the left. All right. What was the t-score? Negative 3.28. That p-value is going to be pretty small. Negative 3.28 for 9 degrees of freedom. 9 degrees of freedom, 3.28. It's going to be between... Oops, no. Going to be between those two guys. Calculator will give you the actual, but I'm trying to go a little faster since we're running low on time. Okay. Conclusion. Conclusion's the same. Conclusion's the same. Oops, not calculation. Conclusion. Conclusion, since p-value is less than alpha level, we reject the null hypothesis. Therefore, we have sufficient evidence to show that caffeine withdrawal is real. Is a real phenomenon. Done. Okay. Yeah.
For matched pairs, are they always going to be means?
Yes.